So I'd like to give you an update on some data sets that are being developed that attest to changes in temperature and in moisture across the Arctic during the Common Era. I'd like to start by recognizing my co-authors, many of them who are in the room today, Nick and Hugo and Fernando, Bronwyn. Thank you for your input to this study. So the Arctic is warming quickly, and as it's warming, the sea ice is pulling back and allowing for more open water, which is generating evaporation, which is driving precipitation. That combined with a greater advection of moisture to high latitudes and with the increasing water holding capacity of the warmer air is all driving increased precipitation across the Arctic in recent times. And we see that represented in a number of the instrumental data sets, including the ERA reanalysis data set for the zone 60 to 80 degrees north latitude. This graph shows for the 20th century the temperature in the black and the precipitation over the 20th century, showing a strong decadal consistency between the two, a positive correlation between temperature and precipitation over the 20th century. And that correlation is degraded a bit when we're looking at effective moisture, P minus E in the reanalysis data set. And I pointed out here some complexity in the correlation. We see that there are decade-long periods in this record where that correlation between temperature and precipitation across the Arctic, I should say effective moisture across the Arctic, is in fact negative or related. And nonetheless, the positive correlation between those two parameters is an overwhelming feature of the climate model output. So this shows for winter in the Arctic, the 20th century correlations between temperature on top and precipitation on the bottom. And looking at the RPC projections, that trend is expected to continue with, again, an overwhelmingly increased precipitation under increased temperatures across the Arctic. The effect is strongest in the winter, but also shows up in the summer within the modeled data. So with that sort of context, that we have this strong positive correlation in the data and model simulations between temperature and moisture, we'd like to ask whether or not the proxy evidence also shows that sort of a correlation. And I'm going to be looking at the full Common Era, the last 2,000 years, at the centennial scale. And to address this question, we have some new products that we can work with, including the new version 2 pages 2K temperature data set. We also have a new borehole temperature reconstruction, which we can use to compare with the calibrations of that data set. And we've taken a first pass at developing a hydroclimate data set for the Arctic as well. So here's the locations and the temporal density of the temperature-sensitive data from the Arctic, looking at polar projection here, where the colors indicate the different archive types. So there's a total of 103 records in the version 2 temperature database north of 59 degrees latitude, and from those we've culled 56 records, which are longer than at least 900 years, to try to avoid some issues with standardization across the time series. So these are all records that have resolution from annual to at least 50 years. And you can see the spatial distribution. I mean, it's dominantly the Western Hemisphere plus Fennoscandia. And the types of archives, and a third of them come from lake sediments, a quarter from glacier ice, and a quarter from trees, and there's some marine sediments here as well. And I've sort of broken down the various sensors associated with each of those archives. So it's quite a diverse range of multi-proxy data. And here's what the distribution of the moisture-sensitive records look like. We've got 43 of them that are also at least 900 years long with a 100-year resolution. These data come from the ISO 2K group that's being led by Bronwyn Konecki, and also the North America 2K effort that Brian Schumann and others have a paper now in review in Climate of the Past. We've also harvested data from the Arctic-wide Holocene data set of Sundquist and others, and we've pulled together some records here for this study as well. The moisture records, we've tried to sort of partition into those that are more sensitive to precip from those that are more, that attest to changes in P minus E or net precipitation, if you will. So sort of it's certainly not a pure precipitation record, but we consider the glacier ice, the accumulation records in the ice cores, to represent more of a precip signal compared to, say, oxygen isotopes in an evaporative sensitive lake. So most of these records, again, over half of them come from lake sediments of various types. Peat humification is another proxy here, but there's a large variety of data. So this graph is meant to just give you a quick sort of visual impression about the trends within the data for the temperature-sensitive records. So the data have been binned at centennial resolution. They've been standardized, some infilling, and I've truncated them at 1900 AD to emphasize the pre-industrial trends. And you can see that sort of the central portion of this heat map shows that the first millennium was warmer than the second millennium, and that shows up in the mean of that cluster. So, excuse me, these are arranged essentially by, according to a cluster analysis. And so the largest group, 40 out of the 56 records, show this overall cooling trend during the last 2,000 years. And then a small portion is, let's say, more random relative to that more coherent trend. And the maps show the spatial distribution. I don't have time to go into that, but suffice it to say that there's no particular coherent trend with these sort of outlier chronologies. We can composite all the records. This is what it looks like. So these data have been gridded on a 5x5 grid. The error bars represent the bootstrap confidence intervals. The temperature scale here is based on sort of a nested approach to calibration using the HADCRU data set at decadal timescales. And that reconstruction then compares to some previous reconstructions for the Arctic, going back to 2009. Here is the decadally resolved records based on just 23 records at that point. And then pages 2K version 1, we doubled the number of data sets and also compared the temperature to, or calibrated them with respect to annual. So notice the scale here is twice that for annual on the right compared to summer on the left. But in any case, the trend, the basic features are all there. We have the overall cooling trend prior to the 20th century, so the medieval bump in the coldest period during the Little Ice Age. I'm afraid I don't have much time to go into the borehole reconstruction. So Hugo and Fernando pulled together 120 borehole profiles, temperature profiles. There's quite a bit of uncertainty scatter among those profiles. The mean is consistent with what the reconstruction shows, where we have a difference of about 2 degrees between the 19th and the 20th centuries. So turning quickly now to the moisture records, they don't partition as cleanly as the temperature records. I mean, most of them show little trend. There's the other half here in the lower part of this scattergram or heat map that shows that the first millennium was somewhat drier than the second millennium. And they all show some downturn. The composites, I should say, show a downward trend in the last few decades. So those are standardized values. In order to calibrate those data sets for the hydroclimate indicators, that's going to be a challenge. We explored a variety of data sets, and this was the most convincing of those in terms of calibration. It's looking at the self-calibrating PDSI for the 20th century, and we've sort of chunked that out into 15-year intervals to show how our P-E, our effective moisture records, compare to that PDSI index. And it hints at a correlation between those two. But stepping back now, looking just at the standardized values for all 43 records, again, gridded, this is what the composite looks like compared to the temperature composite on the bottom, and suffices to say, there's no correlation, no matter which time scale that you're looking at from centennial to millennial. But I did want to explore the sort of the data at a site level that are behind these composites, and I'll explore those first by looking at the overall trend within each of the site-level records and see if we can find some consistent differences. So for temperature on the left, this pie diagram shows that 83% of the individual records show cooling. There are some that show warming. The dark blue indicates that it is statistically significant, so 2/3 of the cooling trends are significant. But when you look at the moisture records, it's much more variable and perhaps not different than random. So there's both 56% show wettening trends, but a smaller proportion of those are really really statistically significant. And then we can break down the moisture records into the precipitation and effective moisture types, and we see that it's really the P minus E, the effective moisture types, that carry perhaps some small significance in terms of trending towards wetter conditions over the common era. And finally, we can explore, say, the warmest and coldest portions of our reconstruction. In this case, we're just looking at the 3 centuries between 800 and 1100 CE relative to the Little Ice Age. It's not a difference. Both intervals are represented here as frequency distributions. So on a standardized scale, the Little Ice Age is clearly colder than the medieval time, and it's representing about a 0.6 degree Celsius difference. But when we turn to the precipitation records, it's much different. The more pure precip records show no difference between moisture values between those two eras. There's a hint in the effective moisture temperature records, the effective moisture records suggesting that the Little Ice Age was in fact a little bit, P minus E was slightly higher, but not significant statistically. So, okay, so I think I've shown that the moisture-sensitive proxy records are not correlated positively with the temperature records, and we've seen this in terms of the centennial scale fluctuations, in terms of the millennial trends, in terms of the cold versus the warm intervals. If anything, perhaps there's a weak tendency towards the negative correlations where the warmer periods tend to be drier. So I think the difficulty is, of course, representing the hydroclimate with such heterogeneity, with noisy data set and in an incomplete sampled data set. There's variable and strong effects of evaporation and sublimation that we're not accounting for, and of course, one of the themes that we've heard in a number of talks is the importance of shifting circulation patterns that overwhelm the direct effect of temperature on moisture. Thank you.
In your maps where you're showing the proxy distribution, it seems like there's a really big gap in precipitation proxies in the Russian Arctic. Is that just because records just don't exist there, or we haven't managed to capture them into our data compilations yet? So what's the potential for filling in that part of the globe?
Yeah, good question. Yeah, no, that's an obvious feature of the data set, is that it really, I've represented them as being Arctic-wide, but in fact it really is just the western part of the Arctic plus Scandinavia. So I don't think the records are there. It's not a matter of having captured them into our data sets. I think that there is potential to develop records in those locations. And so I don't think it's a matter of access, or they're just not there.
Hey, Darrell. I look at the temperature map, and from the end-trend results been published by Rob Wilson and others, there's many more temperature-sensitive records in Siberia than you show there. Is there a particular reason why there's not more records there?
Yeah, I'd have to take a look specifically. So these were screened for just the records that are over 900 years long. So I think a lot of them are going to drop out by that criteria. And again, the focus here was on the full common era, and having a more uniform suite of records that have greater duration, help avoid some of the vagaries with standardization.
Okay, good afternoon, everyone. So I'm going to be talking about one specific proxy rather than the last 2,000 years necessarily. So really, my title should be something more like this. So I'm going to be thinking about, can we use sea salt or sodium that we measure in ice cores as a proxy for past sea ice extent? So your first question might be, why on earth would we think that was a good idea? Why would that be possible? Traditionally, in ice cores, people have interpreted sea salt sodium as coming from the open ocean, which makes total sense. But there's been some evidence that people have really taken notice of recently, that maybe sea ice itself is also a source of sea salt. So the main evidence for this is the fact that we see higher sodium in the glacials compared to the interglacials, and in winter compared to summer. So these are both times, of course, when we have a bigger sea ice extent, when our ocean source is much further away. So it would make sense then to have an actual sea ice source of the sea salt, of sodium. The other source of evidence is if we look at Antarctic aerosol measurements, or snow or ice cores, we see often in the winter particularly that we have a strong depletion of sulfate relative to the bulk seawater ratio. So that's really a fingerprint of the precipitation of this particular salt, mirabolite, which precipitates within the sea ice from the salty brine. Okay. So this is a kind of schematic of the process of producing sea salt aerosol from sea ice. So if you're not familiar with it, we have our sea ice in the center there. We have the brine channels going up. Within those brine channels, we precipitate the mirabolite when we drop below a certain temperature. And then what we're really interested in is actually that snow layer on top of the sea ice that becomes enriched in the brine. It's very salty, but because of that mirabolite precipitation, it's depleted in sulfate, which is really key. So that snow from the sea ice becomes mobilized during what we call these blowing snow events. So effectively, the snow particles are lofted up, and then they sublime, producing the sea salt aerosol. There's some things we really don't know about this process, even though I'm going to show you that I'm modeling it. We need to know more about the snow itself on the sea ice, particularly the salinity and the particle size distribution that's produced during these blowing snow events. And also a big uncertainty, particularly in the Arctic, that I'm going to focus on, is what's the difference between, or what effect does sea ice thickness have on the production of sea salt aerosol from the sea ice. So I'll tell you, I've distinguished between annual and multi-year ice, and said the multi-year ice produces less sea salt, but we don't really have evidence either way. Okay, so this is really a purely a modeling study. I've used an offline chemical transport model called PTOMCAT. You can think of it as a normal kind of climate model. It has a certain grid resolution. And all I'm modeling is the emission of sea salt by from the two different sources, so the traditional open ocean source and this new sea ice source. Within the model, we then transport that aerosol. There's no chemical reactions. It's just transported. En route, it's then deposited by wet or dry deposition. So normally with these models, you look at the concentration or the aerosol that's in the atmosphere. And we will do that, but how I've altered the model is to then look actually at what's deposited at each time step on the ice sheet, on the Greenland ice sheet, so we can then compare directly to ice cores. I should say the model is driven by reanalysis data, and we obviously prescribe the sea ice and the SST, so we're looking only at the moment at the past 30 years just to get a handle on what's controlling the ice core record. Okay, so we'll start off with just aerosol measurements. So what's in the atmosphere? These are 5 different sites from around the Arctic where we have seasonally resolved aerosol measurements. So each graph is showing you an average seasonal cycle of sodium in the black. And then the red lines with the uncertainty bounds are the model results for the whole of the 1990s decade for just the open ocean source. So if we only sourced sea salt from the ocean, that's what we'd get. So we can see there's a big offset between model and data here, particularly in the winter months. At sites such as Alert, we're really missing a big input of sea salt. So this is my best guess so far of the sea ice sea salt source. So we're adding that on there, and we can see that the simulations are much closer to the data. It's not perfect, but it's definitely an improvement. And I would argue from this that we need that sea salt from the sea ice to complete the aerosol budget. We can now do the same for the ice cores. So these are different ice cores from Greenland, which are marked with the green dots. Here the ice core data, the real data, are in green, and the modeled open ocean sources in red. So you can see this time it's not so obvious. We're already about the right level without adding the sea ice. If I add the sea ice on, you can see it adds on a relatively small amount in the winter months. This proportion that it adds on is much greater in the northern end of Greenland, which makes a lot of sense, and reduces to about 10% in the south. So the good thing is that we reproduce the seasonality in the ice core. Maybe the not so great news is maybe we don't need that sea ice source at every site to do that. If we look at the time series of the 90s, in green is the real data, the ice core data. In blue are the simulated records. These are for 4 different cores going from north to south. You'll see I've smoothed the model output, kind of represents that snow to ice transformation. So, and I can actually achieve some good correlation in terms of the annual maximum or the annual mean sodium between the model and the data, which is encouraging and good, maybe quite remarkable actually. Okay, so my next question is if we can use this model to replicate the sodium signature in the ice cores, what does that represent? So there's this question always of, does a change in the ice chemistry represent a change in the source, which may be sea ice or the ocean, or does it represent a change in the transport strength, a change in the storminess? So I've done a sensitivity test to effectively test this. So we run the model for 15 years. The control run has both emissions, sea ice, and meteorology changing in tandem. And then there are 2 runs where one is held fixed and the other is left to vary. Okay. So the results in red will show you when just the emissions or the sea ice are varying, and the results in blue will show you when just the meteorology is varying. So I'm just looking at 3 ice core sites now. These are the ones where we had a decent R-squared with the actual data. These are the control simulations. And in red now is the simulation where we're fixing the meteorology at the year 2000, and we're varying the emissions of sea salt. What you will notice is that every year, every peak looks very similar at the same site, and it may also look similar to the year 2000. If we add on the second simulation where we're varying the meteorology, but we're holding the emissions constant, you'll see it's exactly the same almost as the black line, as the control. It's difficult to see places where they're different. So this really means that the variability recorded in the ice core is controlled by the meteorology and not by the emission strength, so whether that be sea ice or the open ocean. The numbers that you see on the graph are normalized root mean squared deviation. They're the difference between either the blue or the red line and the control, the black line. So you'll see that the blue numbers are much smaller, around 40%, compared to over 100%. So that's showing what we thought, that the meteorology is controlling the signal. So we can look at that number spatially across the whole of the Arctic. for those two different runs. So again, I'll just to repeat, it's the normalized root mean squared deviation between that run and the control. And what you see if we look, Greenland is just down here. You can see when we vary the meteorology, we have this very dark blue color. It means a low value, which means the meteorology is controlling the signal. And on the opposite, on the right-hand side, you'll see in the middle of Greenland, there's a big yellow patch, which means the emissions or the sea ice has very little effect. Okay. I guess this is not too surprising when if we look at where the air masses in Greenland are sourced from, they're not really coming from the major sea ice region of the Arctic basin. So in the winter, for sure, we're sourcing some sea ice aerosol from the Baffin Bay region, but not in the summer. So maybe if we look further north into the Arctic basin, we might get on better if we want to use sea salt as a proxy. So just to back that up then, instead of the dark blue kind of color we have in Greenland on the left here, once you move up to some of those subantarctic islands around the basin there, you start to see a higher value on the left and maybe a lower value on the right. This is the same map of the Arctic region, but the shading is not the same thing, it's different. So this is looking at the annual concentration of sodium in an ice core in the model, and saying what percentage of that comes from the sea ice over the whole year. And as you see, as we would expect, over the sea ice region in that Arctic basin, it's really high. And over Greenland, we have this sharp gradient from a relatively high contribution in the north and getting lower in the south. So again, I just marked on in blue, there's these ice cores that exist around the Arctic basin that might be interesting places to look at the sodium record, providing it's not too melted out. So just to summarize then, I think we need that second source of sea salt to complete the Arctic aerosol budget. The model now works well at simulating ice core sodium concentrations to within a factor of 2 at most sites. The sea ice source contributes to the ice core signature, but it's not required to reproduce the seasonality we see. And there's definitely a north-south gradient in Greenland, so you're better off going north. And our sensitivity test really suggests that in the present day, on an interannual timescale, meteorology is the dominant control on sodium, which is bad news if you want to reconstruct sea ice, but maybe great news if you want to look at meteorology. And then maybe I would suggest that if you want to look at getting a sea ice record, then maybe there are other places rather than Greenland to go look out for. Thank you.
Did you estimate size distribution function? I think it's very different from classical sea aerosol particles.
Yes, I mean we explicitly keep that information of the size distribution within the model the whole way through from emission to deposition, and it works quite well. It matches up nicely with the sparse information we have on the blowing snow source, and also at the other end with Arctic aerosol measurements. In terms of the sea ice source, definitely has more fine particles, and that also does show up in the model, yes.
So I want to take you from Arctic to the lower latitude. It's the steppe in Ukraine, and the history of environmental changes during the last 2,000 years derived from the bottom deposits of the Lake Saki. So here is the lake, which is closed down, and which is located in steppe. All this green area are steppe. And in pollen spectra, we have also arboreal polynomorphs, which arrive from deciduous forest of Crimean mountains. It's only 40 kilometers distance. And pine pollen arrive, I believe, from this big massive of pine forest in the lower reaches of Dnieper. And the other section I will tell about is the archaeological settlement Ak-Kaya, which is located not near the sea, but in the heart of the steppe. So the Lake Saki is not a big lake, it's only 6 meters long and not deeper than 2 meters now, but the deposits are very thick, almost more than 13 meters in places. And from the distribution, you could see that before it was a river which reached Black Sea. Then during the Atlantic optima, the sea came to this valley and it became a gulf of the sea. And then when the sandbar appeared, this gulf became a lake. And lake deposits started to be formed, which had such laminated character, so they are regarded to be wharfs. And starting from the beginning of the 19th century, researchers have been attracted by this archive. I will show you now the bibliography on them. Bibliography on the site. So the first one who counted wharfs and who make paleoclimatic implication from them was Shostakovich in 1934, and his work has been used by Brooks to correlate with Western European paleoclimatic archive, and by Ukrainian scientists correlate with our data. And in last decades there were several projects, one under George Kukla in 19th, and 2 Russian-Ukrainian projects rather recently, where we make new cores in the lake. They were here. This results from this course, where we reach sea deposits with sea shells are already published, but unfortunately we were not able to count as many wharfs as Shostakovich did in his boreholes, but in the borehole of this one, which is located in the place with the largest thickness of deposits, it was possible to repeat the count of Shostakovich, and indeed we found the same number of wharfs, and came to the same date when the lake sediment started to be formed, 4,200 years before. Here we also have C14 dates for the transition from the sea deposits to the lake deposits, but unfortunately the sections are not so complete, and we were not very successful with wharf counts. This is Saki Lake. It has high mineralization. In places it's almost 200 per mile, so it's like Dead Sea, and it is in the beginning of summer and in the end of summer. The main lake is still underwater because it's managed, it's regulated, the water level, but its base are covered by salt pan, and in the other lakes of Crimea, where these reservoirs are not regulated, they still look like Saki Lake looked earlier. So they are just in the second half of summer, in early autumn, they just are covered by salt. And this is the reason why deposits look like this. It was again Shostakovich who firstly suggested that white layers are summer evaporized and black layers are a product of runoff from wet season. Wet season is winter, early summer, June is maximum of precipitation. And here you see this bar is 1 centimeter long. So the lamina are very thin. Average is 1.5 millimeters in thickness. But so it's from the first meter of core, it's starting from 3.1 meters of the core. Everything is laminated up to the depth 6.5 meters. But with the exception of this fine lamination in the core, we also can see pieces 10, 15, 20 centimeters thick, which show different coloration, light or dark. And this is reflected in pollen data as well as the changes in colors. So here is the varv count for the last 2000 from the threshold of era made by Shostakovich, recounted by Kukla, and you can see they are common epoch ages, and you see that in some centuries there are very thin varves, and here, for instance, in 12th, 2nd century, 19th century, there are big thickness of varves. Shostakovich first believed that this is a reflection of humidity, of precipitation. So when there is a big runoff with a lot of precipitation, then the thick varves are formed. And his suggestion has been firstly confirmed by Schwetz, who made a correlation with, for some people, it's fragment, for thickness of Lake Saki varves and indices from Dnieper River runoff. And when we have high runoff, we found direct correlation with the large thickness of varves. Then we decided to check it by pollen data. So it's the vegetational setting of the lake. You see that to the north, where precipitation is lower, there is more drier steppe. In the foothills of Crimea, there is mesophytic steppe, and around the lake, so this dry steppe, mesophytic steppe, and around the lake there are halophytic vegetation on salt soils, and depending on how wet is the spring and summer, we have different production of mesophytic plants, and xeric plants thrive anywhere in this area. So the first step of pollen investigation was to measure the pollen rain over the lake. We did it for 3 years, and here there is an average. And indeed, we see that in spring there is majority of arboreal pollen, and later on of mesophytic herbs and poaceae, and starting from July to September, almost all pollen is pollen of herbs, and mainly of xerophytes, no, of Astracea, but also chenopause and Artemisia. And then we compare this data with pollen analysis of individual lamina, of black lamina and white lamina. Here you see averages. For black beds, we have predominance of arboreal pollen. For white beds, predominance of non-arboreal pollen. And pollen of xeric herbs is much higher in white beds. So indeed, it shows that the white beds are summer vaporized and black beds were deposited during the wet seasons. Then the next step was to analyze the uppermost part of sediments, which we can compare, which we are able to compare with meteorological data. So regarding the annual precipitation, sedimentation rate in the lake, we found the uppermost piece which correspond to the period starting from 1914, then when meteorological observations start on the lakes. And we use the same approach, counting ratio between xerophytes and mesophytes, and compare it with the data from meteorological observation, and particularly for the precipitation during May-July, then when mesophytic herbs can produce pollen. Also, we have markers, not only average sedimentation rate, but we check them with 2 salt layers. Generally, after the lake has been regulated in the beginning of the 19th century, varves stopped to be produced. But there were 2 periods, critical periods in the history of the country, when there were no regulation of the lake, and it was very dry years. So salt layers, are very bright salt layers, appeared in this black mud. And we know exactly when it happened, and we see that they correspond to very low precipitation. So then when we look at the curve of ratio of mesophytic pollen to xerophytic pollen and compare it with precipitation, we see direct correlation. When it's wet, mesophytic to xerophytic pollen ratio is large. When it's dry, is small. So we can use this proxy to interpret our paleoclimatic data. So here is the main section up to 3.5 meters with counted varves, and it corresponds to 2,300 years before present. Yeah, in this complete diagram, I only want to stress that we have impact. We have signature of human impact at the period which were wet. For instance, here you see low xerophytic content, and cereal pollen appeared here. The same here, low content of xerophytic. Agriculture became possible. Juglans was introduced by people who live here. And the other point is that for period which is dated approximately to the Little Ice Age, we have pollen of Betula. This is a plant which does not grow in Crimea, neither in Crimea nor in Crimean mountains now, because it's boreal plant and it's too hot now for it. And then we make such general presentation of the diagram, and the main point is this correlation of some of xerophytes and some of mesophytes. And you can see clearly the cyclicity in domination of xerophytes. Yeah, and each cycle is from 100 to 300 in duration. Only this period is longer, 500 years, which correspond to the 1st century BC and 4th century Common Era. We have unfortunately only 1 C14 dates, but it's more or less judging this era, it more or less corresponds to how it is in varv count. Now the other questions was to try to find connection between proxy of precipitation and proxy of temperature, and from the in some cases, it goes in such a way that a wet period corresponds to cooler conditions. This is a curve for broad-leaved pollen trees, and you see when the amount is small, the pollen of mesophytic is large, and the pollen of xerophytic is small. So when it's cooler, then it's wet. Here it's dry and it's warm. Again here. Okay. But further it became more complicated, and actually we cannot tell for sure about correspondence between these 2 proxies. But there is a very good correlation between thicknesses of varves produced by Shostakovich and recounted by Kukla. When we have wet period by Shostakovich, we have increase of mesophytes, and vice versa for the whole succession. And as a proxy for temperature regime, we use some concept accepted in Eastern Europe about oscillation in level of the Black Sea with high and low stands. Yeah, so for this period which is under investigation, we have several low stands and several high stands by confirmed by different authors. And when we compare them with our pollen data, generally we see that when it's low stand, we have less of broadleaf pollen. When there are high stands, we have peaks in broadleaf pollen, and also little ice age correspond to regression.
Please come to an end, your time is over.
It's okay, so I finished just now. Okay, I would not stop on polymagnetic data, which we already have. This is archaeological section, which show not as high resolution, but still it's good resolution because it's 2 meters for 3,000 years. But generally, what you got from these archaeological sites, this alternation of wet and dry period, they goes well with the Lake Saki, and we have many archaeological sites in the area. And the general conclusion is that when we have wet periods, we have sedentary cultures with some agricultural development, and when we have dry periods, we have only nomadic cultures in the area. So in this dropped vulnerable area,
okay, we'll have to leave it there, I'm afraid, because you've actually gone a minute over your 15 minutes, so we've got to be fair to all speakers. So,
okay.
so thank you very much.
Yeah. I'm sorry if you came here to see Berlin talking about the Mediterranean Sea. I will get you on a journey for a bit of a bigger ocean, so I'm talking about the tropical Pacific instead. So I'm talking about enzoflavors during the pre-instrumental period, and in this talk I'm just gonna concentrate on the different types of El Niño. As you can see already from this like little word cloud, there are a lot of different namings for the same thing, which is a bit similar, but very different from the traditional El Niño as we know. So some namings include El Niño Medoki, Central Pacific El Niño, Dateline El Niño, and Whirlpool El Niño. So they all describe the same but different El Niño as we know it. Before I get started, I would like to introduce you to the big three questions that led into this research. So we're looking at past, present, and future of El Niño Medoki's Central Pacific, or whatever you want to call them. The first question is, were El Niño events any different prior to the instrumental period? What is the recent behavior of El Niño flavors, and what changes are expected in future? So first of all, if we talk about the different flavors, we have to understand them first as we can observe them during the instrumental period. So I would like to point you to two very important aspects of the different flavors of enzo. The first one is the spatial extent. As you can see from this little schematic here, on the left-hand side is the Eastern Pacific one, on the right-hand side is the Central Pacific one. And yeah, you might know the traditional El Niño is pretty strong. We have this particular warming in the Eastern Pacific, a weakened Walker circulation, and massive convection, which is mostly pronounced at the coast or close to the coast of South America. If you now look at the Central Pacific one, it looks very different. So if we look at the Central Pacific one, that has a pronounced warming in the Central Pacific, which is flanked by cold anomalies. So we have cold anomalies to the east and to the west, and some kind of unusual two-cell Walker circulation, which looks quite different from the traditional way. In this case, we have different convection in the center of the Pacific, rather than close to the South American coast, which has pretty much different impacts on the weather and climate system. So just to give you an idea of what scales are we talking about, this displacement of the center of action, so the closest or the biggest warming in the Central Pacific, actually happens 10,000 kilometers away from its traditional place. Just to give you a bit of an idea what 10,000 kilometers can be, that would be as the OSM would not be in Zaragoza, but in San Francisco, or the Indian monsoon would pour down in Morocco, or our Australian kangaroos would hop through the Russian tundra. So it's quite different and has different impacts on temperature and precipitation around the globe.
So how does it look like in real world? So those are composites of Central Pacific and traditional El Nino years, and you can see that the SST anomalies in the traditional Eastern Pacific type are quite pronounced. So we have the massive warming into the east, which extends to the entire tropical Pacific. Yeah, in comparison to that, this is a tradition, or this is the Central Pacific El Nino type, which has pronounced warming only in the Central Pacific, is much smaller of the amplitude. So we're talking about 1 degree, and yeah, so this is how they have a very, very special, different spatial extent. The other aspect I would like to point you to is the different timings. So both types of El Niños have quite a different timings. So this is one example of, yeah, a cross-section through the tropical Pacific. And on the left-hand side, you see the Eastern Pacific type in 1982, 83. So this is a very traditional El Niño event. So we have the strongest warming in the east, which kind of warms up during the course of the year the entire tropical Pacific. This is a Central Pacific El Niño event, and this is quite different if we compare them. This is in 1994, 1995, and we can see that the strongest warming we have in the Central Pacific, which is flanked by cold anomalies to the east and to the west. During the course of the year, we can see here that this warm body extends to the entire Pacific. So we have a warming that warms up the Pacific from west to east. So what we recently see in the 21st century is that we have some unusual trends in our observations. So our observations are pretty much just 30 years, as we can see here. This is just on the left-hand side, a study by Lee et al. In 2010, and it's showing an increase in intensity and frequency of Central Pacific events. So from this plot, you can see there are just a few events. So we need actual paleo data to look at those trends and increases in frequency. So this is going from 1982 to 2010. So is that increase in intensity and frequency of Central Pacific events actually a cause or consequence of either anthropogenic or intrinsic decadal scale changes? So this question we would like to answer looking at paleo records. And that's what we do. So we try to reconstruct both flavors of ENSO using a tropical coral network. As you might have noticed already, so this is the OS2K network of annual dated strontium, calcium, and delta 18O records. But in contrast to those annual linear reconstructions we use that on sub-seasonal scale or sub-annual scale. So first of all, we have to kind of seasonalize our data. So our coral data is seasonalized to March, April, May, September, October, November, DJF, and JJA means, and we use a nested multiple denigration approach to do that. We can't just use Nino 3 and 4 because they're highly correlated, and that's not really good for an independent reconstruction of both flavors. So we're using the NWP and NCT index defined by Ren and Yin in 2011. So those two indices are, you can think of as somehow like a linear 3, linear 4 linear combination. So they're not correlated anymore, which makes it, good to be reconstructed. So how does it look like? So this is our coral network if you look at the second column. But first of all, if you look at the first column, those are the spatial pattern of the different flavors in the tropic Pacific. So the first column on the left-hand side, these are the SST anomalies regressed in a traditional way, and we have the first EOF on the left-hand side and the second EOF on the right-hand side. So we see that this is a traditional warming peaking in, covering the entire tropic Pacific, whereas we have the second EOF, which has, this warm body in the central and is flanked by cold anomalies to the left and to the right. If we do the same now with the proxy network, which is kind of indicated by all those little bubbles scaled to their contribution, we can see that the first EOF of the proxy network of our corals, they're seasonal resolved, show by regressing them on the SST target, pretty much the same pattern as the first EOF of the SSTs. And if we look at the second EOF, we find that the second EOF also resembles quite neat to the pattern we expect from the SST data. So we have again here this warming body flanked by cold anomalies to the east and to the west. So we can be very sure that this seasonal proxy network has some distinct pattern in their seasonal evolution. And to show you this, this is a plot of the second proxy PC. This is during the course of the year, March, April, May, JJA, September, October, November, and EJF. So during the course of the year, we composite all the years of like classical El Niño and El Niño Modokis in red and slightly orange. Here, what you can see is that during the peak season, which is DJF, where we usually have the highest anomalies, we can't really distinguish both of those El Niño types. So there's not much we can see. They don't differ much. But if we look at JJA and SON, we can see massive differences. So these differences in the developing phase are quite significant, and we can also observe that in our target index, which is NWP, which shows the same seasons to be very distinct. So how does the actual reconstruction look like? So this is an example during the instrumental period. So we have both indices, and as you can see in red, this is like the NCT, this is the traditional one. It has much larger amplitudes, and then the NWP, which is the Central Pacific Index. This is just an example of 2000 or 1994 and 1995, and you can see on the right-hand side, this shows you the time evolution of the warming. So we start in March, April, May. We have some warming going in JJA that intensifies SON, and in the peak season, pretty much the entire tropical Pacific warms up to a certain degree. So if we look at that spatially, this is exactly what we see here. We have JJA, a warming starting in the Central Pacific, going to SON, and which intensifies, and then we see in DJF where we have the entire Pacific very warm. So how can we now see what class or what El Niño types we've had? So there are methods we can use from the instrumental and observational studies. We applied to our paleo reconstruction with a sealant resolved a machine learning algorithm which is trained on the instrumental data. So this machine learning algorithm has no idea about dynamics or anything. So we use those classification trees or decision trees or whatever you want to call them to classify them. So this is just an example of such a decision tree. And as we start from the root, we can see in DJF, so we're looking at the Eastern Pacific. If in DJF in the peak season, the Eastern Pacific was unusually warm by 1 degree, we can be very sure that it was an Eastern Pacific El Niño type. If we look down now at the West Pacific, and see if the West Pacific was already very warm by 0.5 degrees, we can then go down to the path where we can identify the Central Pacific El Niño. So this Central Pacific El Niño, if we look down back here, is actually a seasonal evolution of exactly this pattern as we can see here. So our classification tree does not only classify our events, but also makes dynamical sense. So how does it look like? Where El Niño flavor is any different prior to the instrumental period? This is just the frequency plot of the reconstruction and the events we've identified. The red one is the instrumental, the blue one is our reconstruction. You can see we have some ups and downs. We have decadal variability in there we're picking up. Those are the Central Pacific El Niño events. As we can see again, this is the same. So we also have some quite pronounced decadal variability in there. And if we now plot that together as a ratio between Central Pacific versus Eastern Pacific events, we can see that for quite a while this ratio kept being very stable, let's say. We have some periods where we had more Central Pacific events than Eastern Pacific events, which came down here. At the instrumental period, we can see that it ramping up so that we have twice as many Central Pacific ones. And during the instrumental one, we have almost 4 times as many Central Pacific events as Eastern Pacific events. To sum that up, were El Niño flavors any different prior to the instrumental period? Yes, it were quite substantially. Central Pacific and El Niño events were part of natural variability, but now they become more common. What is the recent behavior? Well, we have seen that the timing and the spatial extent is quite important. We have twice as many Central Pacific events right now, and we are in further future, we'll look into the future what changes are expected. So that's still work in progress. So I do have a poster, the 181, so if you want to talk or have questions. Thank you.
So your second DOF with the proxy records, the variability actually looks much larger in the West compared with the Central Pacific. Can you comment on why that might be?
Yeah. I don't know why those, like I expected those like Central Pacific corals to contribute most to this variability, but I think the traditional one is just very strong. We have like 70%, which is explained by the traditional Eastern Pacific El Niño type. So it's hard to get this tiny signal out of it.
Yeah, is your question quick?
Right. Yeah, how do you deal with the fact that you have essentially a coral observing system that's biased to the Western Pacific, so it's essentially not designed to pick up Eastern Pacific El Niños?
Well, I'm not sure what it was designed for, but...
Well, yeah, I'm not in touch with the creator. But I've tried this before, and the problem always was that you don't have enough data from the East, and you have 2 degrees of freedom. You have, you know, trying to have Central and Eastern Pacific El Niños, and essentially they more or less look the same unless you have some data from the East.
Yeah. Well, we have those 2 sides at the East, which is not much, but it is something. We try to overcome that by like adding some temporal freedom of degrees and some spatial ones. So that's how we tried to add more information into a system.
Tree ring records are the most prevalent source of information on interannual variability of climate over the last couple of millennia, and they contribute very largely to the sorts of reconstructions that we're using for model evaluation. So it's disappointing, and I'm looking here at the diagram up on the right there, I guess. It's disappointing that the uncertainty in our tree ring reconstructions is sufficiently large that we cannot constrain the model simulations that were made by CMIP5. So the diagram at the bottom is showing you that there's so much uncertainty in the reconstructions that we can't discriminate between climate simulations with our current data. So it's urgent that we do something about improving the uncertainties in these reconstructions. And I want to look here at some of the assumptions that go into the tree ring reconstructions and to see whether we can deal with them in a little bit of a better fashion. And the 4 assumptions I'm looking at are ontogenetic or growth trends can be removed through some kind of statistical smoothing, that there's stationarity of the climate control on tree ring growth, that non-climatic factors have no influence on growth, and that stem allocation is somehow a constant proportion of the total productivity. I'm not going to belabor this, but we've been using techniques to smooth out growth trends or aging trends in the tree ring records. There are multiple methods of doing it. The choice of the method that you use determines your final result. In terms of stationarity, we assume that we can establish a relationship in one period and then apply it forward and backwards in time. This is a plot that shows you the correlations for Picea tree ring widths between 1940 and 1970, where the dark red dots show a strong positive correlation with summer temperature. The dark blue plots show a strong negative correlation, and the kind of wishy-washy ones in between show no correlation at all. If you look at the bar plots on the top there, you'll see that the strongly correlated with summer temperature sites have become less correlated as we move towards the present. So I'm comparing here 1940 to 1970 to 1970 to 2000. They go from being significantly positively correlated to losing any significant correlation with summer temperature. The plot on the bottom shows you precipitation and shows that over that same period, the correlation with summer precipitation increased. And these plots here show you the 30-year time moving windows of those correlations, and you see there is no stationarity in the correlation of tree ring width for Picea in this region with summer temperature. I could actually demonstrate this for other climate variables, but I don't have time. Okay, the next thing is we make an assumption that nothing else influences tree ring widths. This is a study that was done looking at tropical tree rings, and where they're showing that CO2, the change in CO2 over the last century, has had a profound effect in the top on the CI ratio, which is a measure of internal CO2 concentration and tells you something about photosynthesis. In the middle on water use efficiency, how the trees are adapting to drought, and on the bottom, tree rings. The first two show a significant correlation as CO2 increases. Tree ring width shows no correlation with CO2 through this period. The only way you can explain that is if the trees are somehow changing their carbon allocation from the stems to other parts of the tree. Here's a simulation on the top that shows model simulation versus observations, and you can see that at the end there's a discrepancy between what the model's showing or predicting and what the observations are showing. In order to match those two records together, we have to change allocation. We have to increase the allocation to below ground roots to take up more water and to take up more nutrients. If we do that tuning and then we ask ourselves, why is that allocation change happening? You can see that about 70% of the signal comes from the change in CO2, but a significant proportion of the signal, if I can get this to work, whoa! Okay, I won't touch it. A significant proportion of the signal also comes because there's changing allocation in response to drought. This all suggests to me that statistical relationships between tree rings are not going to be the way that we get the best story out of our records, and I'm going to suggest an alternative method, which is to use a physically based tree growth modeling approach. So here I'm showing a very simple model. It's a coupling between a light use efficiency model, the P model, which takes into account climate, CO2 concentration, latitude and elevation effects, and produces a simulation of gross primary productivity, which is then fed into the T model, which is a model of carbon allocation and functional geometry. So this T model allocates carbon between leaves, stems, and roots, and it does so following known relationships which have been used in the forestry community for a long time in terms of functional geometry. That functional geometry relationship allows us then to tell how much carbon is being used by roots, how much by leaves, and therefore how much there is in the stem, and that enables us to stimulate ring widths. Now, we can use this model to simulate productivity changes and tree ring changes. Here I'm showing you a simulation driven by climate model outputs from the IPSL model. This is the productivity part, so this is the P model part. This is the end of a millennium long run, and it shows you GPP in 1850, which basically shows that the model is able to capture the spatial patterns in GPP, and it's done it through a millennium long simulation. So we can look at the millennium-long simulation. That's what's shown on the top there, and you can see variability in productivity through time, with increased productivity during the medieval warmth anomaly and reduced productivity during the Little Ice Age, and the map at the bottom shows you the spatial patterns in that. So going back to the tree growth modeling part, this model has been developed and applied for a number of different conifers. I'm showing you the pretty pictures here to keep you awake. The latest result from this is Cedrus atlantica from Morocco, which shows a good correlation between the model and the observed tree rings in that site. So the model is able to reproduce the interannual and decadal variability in tree rings. It's able to do it by being able to model explicitly ontogeny as a function of geometry. Here I'm showing a single tree, and at the top there, get this to work. Here, no. Okay, a single tree at the top, and you're seeing how ring widths increase during the early phase of the tree's growth and then gradually decrease. We've tested this out in Chiangmai on pinus trees, and there we had a very vigorous test of the model because we had 3 cohorts of trees, some of which were 150 years, some 100 years old, and some 50 years old. For some reason, the poor old trees in the middle were starved at some stage in their growth, and they had much lower rates of growth than the other 2. And furthermore, you can see if you compare the charts on the your right-hand side there, we can get that growth rate even though they had different histories through time. So we can do ontogeny, and we do it through geometry. And one point I want to make here is that it's not age-related changes in tree ring width, it's size-related changes in tree ring width, which is why we can get this middle group here. This is also from Chiangmai. It shows that we can look at the individual climate controls on tree growth. The observations are at the top, the simulations at the bottom. We reproduce the individual climate controls. These are the residuals from a GLM, which show you the independent relationships of tree rings with each of the climate variables, showing a positive relationship with light availability, a positive relationship with moisture availability, and then the panel in the middle is a negative relationship with temperature, which at this site arises because as temperature increases, so atmospheric drought increases, VPD increases, and that limits growth. Okay, going back to my productivity diagram here, we can now show from this what the controls of the changes in simulated productivity are, and we can show that the model is sensitive to multiple climate controls. So here I'm showing the correlations through that 1,000-year period with 4 major climate controls, PAR 0, which is the growing season light availability, mean growing MGDD 0, which is the mean temperature of the growing season, cloud during the growing season, CL, and then this vapor pressure deficit. And the relationships we're showing here are the combined relationships of these 4, which are producing the changes in tree growth. But more importantly than that, we can see also that there has been through this millennium an impact of CO2 on the tree growth. So the plot here is showing the correlation with changes in CO2 on tree growth, which is always positive. So when CO2 is increasing, then tree growth increases. When CO2 decreases, then it decreases, but shows spatial patterning. So the impact of CO2 is much less in the high latitudes than it is when we move towards the more arid interior. So the model is capable of doing the multiple climate controls, and it's also capable of doing CO2. Not to belabor the CO2 thing too much, but I want to say we've applied the model to look at trees at the last glacial maximum. The last glacial maximum is very difficult for trees because the CO2 was very much lower. That meant, and isotopic information shows us that the glacial CI-CA ratio was the same as today, i.e. the internal concentration of CO2 was much lower, and that means that the trees were at virtually starvation level. But we know that glacial growth ring width was similar today at this site from La Brea. And the reason that that's the case is because the trees were allocating less below ground. So the plot here shows what happens to both leaf area index in green and below ground allocation in red as you reduce CO2. So we're able to simulate the CI-CA ratio directly from the model, but in order to get this continued tree growth during the last glacial maximum at La Brea, we have to change tree allocation, carbon allocation, and we have to remove allocation from the roots. And we're able to do that because, in fact, in California at the last glacial maximum, it was wetter than today. So I want to finish with 4 take-home messages. The first one is that plants are clever. They optimize their performance to maximize their growth. And when I say growth, I mean overall growth, not just stem growth, but the total carbon that they're taking up and growing with. The second thing is that trees are not foresters. They do not think like foresters. Foresters want to optimize stem growth, But trees want to optimize total growth. And if it's necessary to put more mass into the roots in order to get more nutrients or to take up more water, they will do that at the expense of stem growth. I think, and I know that everybody has been thinking about this, many of the assumptions that we have that underlie our statistical reconstruction techniques are violated under a changing climate, and we have to take that into account, particularly as we go back in time. And what I'd like to suggest that one way forward here is to use a mechanistic productivity and tree growth model based on optimal allocation theory, which therefore takes into account the fact that trees are clever. Thank you very much.
Some GCMs currently in existence have land models that actually do this kind of thing. So they model carbon allocation, perhaps not in such a sophisticated way. Would you care to comment on the differences in terms of modeling framework and performance, if you know, for how they model carbon allocation versus how you are doing it?
So effectively what we're doing here is focusing on trees as individuals. And so we're using species-specific parameters to deal with the carbon allocation side of it, which is not the way it's being dealt with in land surface models, for example, at the moment. And that means that this is more of a forward modelling tool for the paleo community, I think.
Have you run the model forward using RCPs and climate projections?
No, we've only just finished doing the last millennium simulations. No, we will do that, but I don't believe in running stuff into the future until we've really tested this stuff in the past. So we want to test this by showing that we can reproduce the tree ring series. We also want to show that we can test this, the productivity part of it, by comparing with the peat records that Zick has put together. So I want to do a thorough testing of the model over the last millennium, and then we'll run it forward and see what happens in the future.
Good afternoon. So we are going now to again to the regional climate and regional climate variability. And so we have heard during the conference now a lot of new reconstruction, also about new ways to also have an assessment of regional climate change. This is just one example here, the reconstruction for Europe. And you can have it traditionally as a regional average, and you can have also spatial reconstruction in 5 by 5 degree boxes. And this is going on. We have seen the drought atlases popping up with cover subcontinent or continental scales. And once we see that, and once we can use that, we can also ask questions. The old question that we are faced with in the common era, the forced versus internal generated variability, but also then to look into how can we explain specific patterns, spatial patterns of variability and teleconnection patterns. Why do we find correlation between areas together and so on? And of course, if we can connect what we see in the reconstruction with, for example, circulation changes in the atmosphere, we can have also a chance to understand the relationships between temperature and hydrological variation. That was the issue that was brought up yesterday, for example, by Frederick Lundquist. Now, if we take this Lutherbacher reconstruction and do a very simple exercise here in EUF, showing here the first and the second EUF. And so the first one is more monopole, and to say this is partly by construction, of course, but it gives some interesting aspects here. And actually, if you look at the right side of the plot here, you see this pronounced north-south temperature gradient, and you saw something right similar on yesterday's poster by Mary Gagan, where she discussed this as a kind of very prominent mode of variability. The question that we want to ask here is also to concentrate on this more monopole mode, and for one question is it really just the expression of the global mean surface air temperature that we see here? And I will try to convince you that it's not. When we do a similar exercise like that with the data from the climate model. We use here the Max Planck Institute model, where we have 3 realizations for the last millennium. We get relatively similar picture here, particularly when we degrade the model to this 5-degree resolution of the reconstruction. I don't show that here, but rather go here to a situation where we subtract from the surface air temperature the northern hemisphere mean, just in order to concentrate more on the aspects of internal variability. So we also assume that the northern hemisphere mean is an estimation also of the forced variability. But what you see here, we still get this kind of separation where this pole with this monopole, even though the strongest loading is here seen in that simulation more in the northeast of Europe. But you still see kind of this separation. And when we connect this EUF time series with the just the field of surface air temperature itself, we get the left picture here, where we can see that this is has the highest loading over Northern Europe, but it's extended also into the Arctic. It has a negative cold situation into the east, and if the plot was bigger, you would also see another warm splash if you go further to the east over Asia. And so if you see some connection like that, warm, cold, you can go assume that this is a feature comes from planetary waves, and some people call such a feature that you see on the right-hand side. So this is the geopotential at 200 hectopascal upper troposphere with a wave train in Rossby waves, and some people call it also the circumglobal wave train. This is in particular when you this is now the right plot here, is the first EUF of the geopotential 200 calculated in a certain way as it was defined by some in the literature to characterize the circumglobal wave train. So we see the pattern that we get here in connection with the European temperature, and this wave train pattern is quite similar, and so we can therefore say that this determines quite a bit of spatial variability and spatial covariability over the continent. The temporal correlations shown here in black is just the temperature area mean, and then we have the first EUF, and then these first EUF of the geopotential. So they are, of course, quite significantly correlated. In particular, also even if we don't subtract the northern hemisphere mean and just connect the time series of the first EUF, the geopotential, with the field mean, we see that still roughly 35–40% of variability can be connected to that. What is interesting here is, so I said I concentrate on internal variability, but we see that when there is external forcing, it acts in a way that it more or less disturbs this relationship. So we highlighted here just, for example, 2 bigger volcanic eruptions where we see that the curves don't agree there very well, and it's probably a good idea to understand how that works for future work. So these patterns, of course, have surface expression, not only in temperature, but also in sea level pressure. We see this kind of very strong blocking high over Scandinavia, and that is connected with dry conditions there, and in particular with a relatively zonally banded structure in these features, in particular for precipitation. And so we have not done that there, but it's probably quite valuable really to look into reconstruction if we can find hints of these zonally structured changes in precipitation patterns. Could be even in documentary, but we haven't gone that far as well, and the paper yesterday by Frederick Lundquist probably raised also some question how reliable the model simulations are. But I think we have to do these kind of simulation and analysis to understand what we see also in reconstruction, and maybe also what we see, what we don't see in the models where the models fail. So coming now to the next question, what modulates this variability? So if you have such a Rossby wave train somewhere, the question comes, where comes the energy from? Partly it's, some studies said it comes from the tropics, and other studies connected to the Atlantic multidecadal variability, where some studied related to the tropical part and others to the extratropical part. Another story was suggested by Sarto in a recent paper, 2014, meaning shift in the Gulf Stream and associated diabatic heating. And the other question is, seeing these low-frequency variations and maybe some connection with the ocean, the question comes up, is the AMOC involved? In particular, we will have 2 more talks on AMOC in the next half hour. So looking at that for the ocean, this is now the composite based on our European temperature EUF and the sea surface temperature. To the left, where we see quite pronounced signal of temperature in the region of the Gulf Stream and in the high northern latitude. So there seems to be some connection with the Gulf Stream and also with ocean heat transport. And the right, you see the ocean atmosphere heat transfer, heat flux, where blue colors indicate heat transfer from the ocean to the atmosphere. So that's what we are looking for sources. And you see quite prominently here the region of the Gulf Stream, partly also in the northeastern Atlantic. Not so much in the Arctic, where also other studies have seen kind of or suggested connection with heat fluxes in the Barents Sea. So the AMOC connection, so if we use the traditional 30 North AMOC index and just composite or regress SST, we actually do get in the model the familiar AMV pattern here to the left with relatively strong warming in the subpolar North Atlantic and then this comma-shaped part in the eastern part of the Atlantic. When we do the same thing with the AMOC at 45 north, then we get a pattern that looks pretty similar to what we saw on the previous paper from the composite with our temperature EUF. So it could be that for this part of the modulation by the ocean, the gyre system and the AMOC in higher latitudes is more important. So that brings me already to the conclusion. So we have seen that quite a substantial part of European summer climate variability is related to an atmospheric circulation pattern modulated by planetary waves. And this introduces pronounced zonally orientated patterns in temperature, precipitation, and over Europe and the Eurasian continent. Right now, I would say the most likely is that it's triggered over the Gulf Stream, but we are still in the work of nailing that down further down, doing more sophisticated analysis with wave sources and so on. And we have seen that similar patterns of variability also works in the unforced PI control simulation. So we assume that this variability that I'm talking about is mainly internally generated, but there's an interesting relation to the external forcing that needs to be explored. One of the motivation actually of the study was that we saw in some reconstruction of relatively remote region, in particular the Alps and the Altai, in the paper by Bündgen et al., some co-variability that could be explained with such temperature pattern. So, and of course, this is a model study, even though the motivation was European reconstruction, but it is probably a good idea to go now into more of the reconstruction, particularly connected, as Frederick suggested, also with the precipitation and drought indices that we have now. Thank you.
I just wonder about the explained variances comparing the model results with the reconstructions. And I just think, like, do the reconstructions really explain the first two EOFs almost over 90% of the variance? This seems to be quite high even for summer temperatures. So I doubt a bit more the reconstructions in this case than the model results.
Yeah, so you're referring to that. I don't have the numbers here. I really don't have an explanation for that. So if we degrade the model simulation to the 5 degrees, so this comparison, so we have in the reconstruction, it's like 70 to 25 or 30 or something, and in the simulation, it's more like 40 to 25. So I cannot really explain why, what the reconstruction, somehow some smoothing in the reconstruction would emphasizes more the low frequency, maybe the forced part of it. That would be a problem.
Thank you very much to the conveners for the chance to speak to you today, and I'd like to just thank the co-authors listed here for their contributions to this work. It's largely come about from an NSF grant to myself and Darrell, and also more recently a European Union grant. And so what I'm going to be talking about today is the Atlantic meridional overturning circulation that we can see in this schematic here by Stefan Rahmstorf. And the AMOC is important because of its role in terms of heat transport in the northern hemisphere. And so in the figure you see the red surface currents that transport warm salty water northwards. It then goes sinking in the Labrador and Nordic seas, and then it returns back at depth. And so this is thought to play an important role in past climate changes because of this heat transport. And for that reason, we're also concerned about it in the future with the issue that things like melting of Greenland, increased precipitation at high latitudes may weaken this circulation. And so we're worried about it reducing or collapsing in the future. For that reason, a large amount of money has been spent into trying to monitor what's been going on with the AMOC in the recent past. And so in 2004, there was an array put across the Atlantic at 26 north, monitoring the strength of this circulation. And the results have been quite surprising, not least because of the huge variability they see in short time scales, but also as the record's been lengthened, we see this ongoing decline at a rate that's about 10 times faster than models are predicting. But with such a short record, we don't really know if this is just part of natural multi-decadal variability, or is it part of this expected weakening of AMOC. And so we need a paleo perspective to place this in context. And in the framework of this session as well, we'd really like to have a better understanding of the role of AMOC in past climate events, such as the Little Ice Age or medieval climate anomaly. And so that's what we've been attempting to do. There's a number of approaches that have been put forward about how we might do this. Some work by Rong Zhang has suggested we can use this AMOC fingerprint on upper ocean temperatures. And this is the fact that with a stronger AMOC, there's a characteristic temperature fingerprint in the upper ocean. In this case, the T-sub refers to temperatures at 400 meters. And you see a warming of the subpolar gyre with a strengthened AMOC. And because of changes in the position of the Gulf Stream, you actually get a southward shift of the Gulf Stream during a stronger AMOC, and you get this cooling off the northwest Atlantic shelf. Related to that, this paper came out a couple of years ago now by Stefan Rahmstorf and others, using a similar technique to try and reconstruct changes in surface temperatures and relate them back to the AMOC. And this suggested that there's been an exceptional weakening in the recent past. One possible criticism of this is arguably that it mainly relies on the terrestrial network of data, and the marine evidence, or the marine temperatures are largely inferred from that. And so it'd be really great to get some marine evidence to try and support this, and that's what we've been trying to do. And so one other approach we can do, instead of a temperature proxy approach, is we can look at changes in deep Labrador sea density. This is an approach that's been put forward by John Robson in recent papers. And what we see from model studies and to some extent in observations is that changes in the density of the deep Labrador Sea, shown up here, correlate very well with changes in the AMOC. And so they've used this to extend the rapid period, which is just this very short period here, and instead look at Labrador sea density changes as a predictor of AMOC changes and extend it back through the instrumental record. One feature we're going to make use of is the fact that these density changes in the deep Labrador Sea, they propagate very rapidly down the western boundary, and this leads to a change in the cross-basin density gradient that drives a stronger AMOC, but it's also associated in models, and through simple theory, we'd expect a speed up of the deep western boundary current. And so the deep western boundary current is a major component of this return flow at depth of the AMOC. And we're just seeing this increased velocity with a greater deep Labrador sea density in this model simulation at least. The difficulty is that it's very hard to reconstruct density of the ocean, especially at depth in the past, but what we can do is we can reconstruct changes in velocity of deep sea currents relatively easily. Just to finally, in this introduction, I think it's important to realize that these two different types of approaches are in fact coupled, the temperature and the boundary current response, or the deep Labrador Sea changes. And so this is just some modern observational data here. The red line are changes in the deep Labrador Sea density over the recent past, and then there's this 10-year lag in the response of the temperatures you see in the Northeast Atlantic. So in essence, what happens is you have convection in the Labrador Sea, you spin up the AMOC because you're forming this dense water, and after about 10 years or so, the warm water is making its way up through the subpolar North Atlantic. And so on to our methods for paleo-reconstruction. First, we're using a couple of cores located in the deep western boundary current at about 1.7 and 2 kilometers depth. And we're going to reconstruct changes in the strength of this deep western boundary current as a proxy for deep Labrador Sea density and by inference, an indicator of AMOC. We're going to use sortable silt analysis, which looks at the 10 to 63 micron fraction of the sediment, and there's a paper in revision at the moment that's doing some modern calibration of this proxy to flow speeds. So onto the data. So what we can see here in the top panel, in the blue is our reconstruction of changes in deep western boundary current speed over the last 120 years or so, and that's being compared to modern observational data in black of changes in Labrador Sea density. So that's the actual measurements of Labrador Sea density. And so over the last 60 years or so, we see a good agreement between our inferred flow speed in the deep western boundary current and Labrador Sea densities. In the bottom panel, we're comparing our deep western boundary current records to changes in the surface temperature of a subpolar gyre upper ocean heat content. And that's the red line shown here. This is using a data reanalysis set, the EN4 data, and then kind of hiding behind it, it matches quite well so it just disappears. There is a green line hiding back in here, and this is it's the first EOF of the upper ocean temperature that's been suggested by Rong Zhang as this AMOC fingerprint. And so this is showing this coupling between the deep western boundary current and the changes in the upper ocean heat content. Just looking at that in another way, mainly just because I find it cool to be able to play with paleo data and modern observations. This is just showing the correlation between our grain size, our deep western boundary current speed, and changes in the upper ocean heat content. And what you see is there's this lagged response of the upper ocean heat content. You see these heat anomalies developing, and then they propagate in this kind of comma shape going around the subpolar gyre as time progresses. And then you also see this cooling off the northwest Atlantic slope that we'd expect. I mean, this has important implications in terms of predictability of what would be happening in 10 years' time in the Northeast Atlantic in terms of fisheries and things. We know what's happening in the Labrador Sea now. We can tell what's going to happen in 10 years' time. So there's economic reasons for this, the importance of this. What we can do, obviously, with sediment cores is extend further back than the instrumental record, and this is what I'm showing in this top panel here. And what we can see here is that we were previously just looking in at this little section here of the last 120 years, and we can see it's quite different to what we've seen over the last 2,000 years. There appears to have been a shift to a weaker deep western boundary current that occurs about 1850, and we've replicated this in another core. Using calibration, this would represent about a 20% change in the flow speed of the deep western boundary current that you potentially could scale up to AMOC with many caveats. And so it's, for context, prior to 1850 AD, I'd probably say that AMOC was more similar to, say, the state of the 1990s when we were having this strong deep convection taking place in the Labrador Sea. It's probably interesting as well to note that although we do see some earlier variability, there's not very strong or very clear correlations between things like the Little Ice Age medieval climate anomaly. I'm not going to talk about that further, but the major feature is really this weakening of the industrial era. We think this is related to changes in Labrador Sea convection, and some support for this comes from published data that's looking at near-surface temperatures in the Labrador Sea. And so if you have weak convection in the Labrador Sea, you don't get this wintertime cooling and freshening of the water column. And so without convection, you get warmer and saltier water. And this is what's seen in this record from the Labrador Sea. So it seems as if this weakening of deep western boundary current has been driven by a weakening of Labrador Sea convection around about 1850 or so. Moving now to the kind of a temperature fingerprint. As I said, you expect with a change in the AMOC to get a temperature fingerprint off the Northwest Atlantic Shelf. And so we've looked at a number of published records with improved age models and some new records, and basically sites where we'd expect to see a warming with a weakening AMOC, we see that, and sites where you would expect to see a cooling with a weakening AMOC, you see a cooling. And so there's some nice support there. We can also take a basin-wide approach, and we can use forehand-based records. We're using forehand-based records because we're more interested in subsurface temperature rather than true SST. We think it'll give a better AMOC signature. We can compile existing records, and we can look at what's going on in the the northwest, and then in the northeast. You see those contrasting trends over the recent past. And together you can use those to put together an AMOC index that's shown in this panel here. And the orange record is this earlier record, very totally independent reconstruction of Stefan Rahmstorf and others. And on the long time scales, we're in excellent agreement. So we've seen multiple lines of evidence that suggest there's been this shift in Atlantic circulation and weakening of the AMOC around about the industrial era. On shorter timescales, there's some differences between our reconstructions and the Rahmstorf reconstruction. That's likely due to complicating factors on these short timescales, things like an imprint of NAO. And so what might be causing this shift at the end of the Little Ice Age and onset of industrial warming? I can't find any particularly strong evidence in terms of changes of atmospheric circulation. That's not to say it wasn't a role, but there's no convincing evidence I can find yet to say it's the leading contender. And that leads me to think it was probably more related to export of fresh water out of the Arctic Ocean. There's historical and observational records of very thick sea ice in the Arctic during the late 1800s, early 1900s. There was also extensive ice shelves up in the Arctic. So we know there was a lot of fresh water in the Arctic in the Little Ice Age. It's not there today. It had to come out at some point, and it very likely had an impact on the overturning circulation. You can do some back-of-the-envelope calculations on the relative fluxes, and they agree with kind of the generally agreed sensitivity of AMOC, and we'd expect an impact of that. Maybe in the 20th century, as Stefan Rahmstorf suggested, Greenland ice sheet melting may have also contributed to keep it suppressed. And so just to summarize, we need these extensions of modern observations to place them in a longer-term context. We've used flow speed changes in the deep western boundary current as a proxy for AMOC, as well as sea surface temperature or near surface temperature fingerprints. And both of these approaches suggest a weaker AMOC at the onset of the industrial era, likely caused by a weakening of Labrador Sea convection. It really highlights the anomalous nature of the world we've been living in compared to the last 2,000 years. If you just looked at the last 50 to 100 years, you get a very different state to the last 2,000 years. And the other point to make, the final point, is that a lot of the climate models, or all the climate models, don't really simulate this to this extent. And so it's either that they're maybe missing certain processes, do they have this very thick sea ice in the Arctic, or it's arguably that they're not quite sensitive enough to freshwater forcing. Thanks very much.
I'm just interested in this time lag between the changes in circulation and the warming, which you've variously had as 10 and 12 down there, and which I think may change depending on the climate state. So I wonder if you had any comments about, do you expect that to be longer or shorter, for example, during the Little Ice Age?
Good question. I suppose it will have a slight dependence on the strength of the upper ocean circulation and the time it takes for those anomalies to be transferred. I wouldn't have thought there'd be a huge change, though. The 12-year, it falls out both of sort of modern observations and then our reconstructions of the last 100 years. And then obviously as we go further back in time, if we're looking at marine records, for more or less all marine records other than, say, some layer clams, our errors are never going to be good enough, so we won't be able to tell, sadly.
David, you linked the change at the beginning of the Industrial Revolution to freshwater input from coming out of the Little Ice Age. But that's a very strong signal, and well, the Little Ice Age was a cold phase, but was it that special in the Holocene that you have this very distinct peak in your record, which there's nothing similar in the past 2,000 years, and probably also nothing similar in the last 10,000 years. So what makes it so special?
There's a number of points there. I would say there may be, if you come to my poster, there probably were some similar earlier events. If you just go a little bit further back, you'll see some. And I mean, arguably, there's some of these events here, which are almost comparable. What was the other point?
Maybe I could say you guys can discuss it in the poster session, and we'll just quickly have this question up the back.
Thank you. Hi, Dave. Nice talk. Just wondering, I'm very interested in the modern calibration that you and Nick McCabe are doing for the soluble silt and flow current speed. So can you apply that modern calibration curve to your soluble silt record over the Labrador Sea, or do you still have some reservations of it because of the caveats, known caveats of soluble silt proxy?
I missed a little bit. I can and do apply this to these sediment cores, and it gives reasonable numbers for the core top, and the magnitude of change, say 20%, is, say, in agreement with the kind of magnitude of changes that Stefan inferred in his work. And we've applied it to a number of places, and it seems to work very well. My one caveat for the community is don't apply sortable silt anywhere and everywhere. You've got to be careful. There's only certain sites where you've got strong and relatively steady deep boundary currents.
My talk follows beautifully after David's, but first let me acknowledge my co-authors here, especially my PhD student Levke Cesar, who has done most of the hard work, the number crunching for this study. David saved me quite a bit of time by already referring to our paper that appeared 2 years ago, where we were looking at the observed warming trend since the year 1900 until the present year, which indeed is a global warming trend almost everywhere, except for this one special region, the subpolar North Atlantic, where there has been an observed cooling during this time period. And in our paper, we attributed that to a slowdown of the Atlantic meridional overturning circulation, or AMOC. And that's because in this region is exactly where the climate models show a cooling when you slow down the AMOC. And this inspired us to define an AMOC index, which is based on the anomaly of the subpolar Atlantic temperature relative to the average northern hemisphere temperature. So the difference between what's happening in the subpolar Atlantic and the rest of the northern hemisphere, we think, is dominated by changes in the AMOC. And this is what this AMOC index showed when we define it in this way. It shows a general decline in the AMOC corresponding to that cooling in the subpolar North Atlantic, and in blue and in red you see the instrumental data, the Hadley Center data and the NASA GISS temperature data. But there's also an additional interesting curve here. It's proxy data from deep water corals and 15 data. And at this stage, I just like you to remember this curve and the fact that it agrees quite well with the AMOC index from the instrumental temperatures, including that low in the roundabout 1980, 1990, and then a recovery up to the year 2000. And I will come back to those coral data at the end of my talk. In our paper, we extended this series using Mike Mann's multi-proxy data for the last 1100 years. And there we see, first of all, at the end of this, the thin blue line overlain there is the instrumental data, and the proxies and instrumental data for the period of overlap agree quite well. And they show, as I showed in the previous graph, this decline in the 20th century. And the proxy data would suggest that this is actually unique in the past 1100 years. Now I want to come to some further work that we've done since that paper was published, and the first is relating to the question, how good is this AMOC index in representing the actual AMOC? And there we turn to the CMIP5 climate model ensemble, and here the number crunching and the graph was done by Alex Robinson, who is somewhere in the audience. I see him up there. And this shows this trend since the beginning of the 20th century on the x-axis for the AMOC index in the model, based on these surface temperature data, and on the y-axis the actual AMOC, which in the models, of course, we know, unlike in the real world, so that's the advantage of the models. And you see there's a very strong correlation of 0.9 here with an R-squared of 0.81, which means that the AMOC index explains 81% of the variance in the actual AMOC trend in these climate models. So this is encouraging and reaffirms that the AMOC index as defined by us actually has some utility in reconstructing the real AMOC. And now we can put the observed value of the AMOC index decline from the observed sea surface temperature data on this, and with this calibration translated into an AMOC anomaly. And the AMOC trend inferred is about 1.5 Sverdrup per century, and because this is actually a trend from 1880 to 2016, this translates into an overall decline by about 2 Sverdrup, which is between 15 and 20%, just like David said. Now, we're working with folks from GFDL, and Eric Galbraith yesterday mentioned that they've been slaving away since the 1970s with 100 people perfecting climate models, and this is the latest, highest resolution implementation of this, and it shows you very nicely how the model produces the Gulf Stream here and the colder water from the Labrador Sea moving south inside the Gulf Stream. And when this model has been used for a CO2 doubling run. It's a coupled climate model with a very highly resolved ocean. And this is the result. It was published last year by Vincent Saber, who's also one of our co-authors on this new work. And as a response to CO2 doubling, this model shows a cooling in the subpolar North Atlantic, shown in blue here. But it doesn't only show this cooling there, it also shows strongly above average warming of the United States coast there. And both of these features are, according to these authors, and also I'm convinced that's right, they are both linked to a slowdown in the AMOC in the model. And there's also an established physical mechanism behind this, identified in this paper by Zhang and Veles in 2007, in that at the point where the AMOC crosses under the Gulf Stream, the vorticity dynamics of this will make the Gulf Stream shift northward when the AMOC weakens. And that is exactly what you can see here. That's a northward shift in the Gulf Stream in response to AMOC weakening. This is another look at the same model data. Here we have shown it by dividing the local temperature trend over that model run by the global mean temperature trend. And so in blue, you see everything that has warmed less than the global average or cooled. And in this orange-red, you see everything that has warmed more than the global average trend in the CO2 doubling experiment. And I think now you can very clearly see the pattern of blue and red here that is indicative of a northward shift of the Gulf Stream. Incidentally, I didn't plan to talk about this, but since Melanie mentioned this in her talk yesterday, that she found in stadials warmer temperatures in the Norwegian current than in the interstadials, this model actually predicts a warming along the Norwegian coast when you slow down the AMOC, which is quite interesting. I think this warrants some further investigation. So I would argue there is a very distinctive fingerprint pattern of an AMOC slowdown that we see in the model here, and we were interested whether we can see that in the data. And there we turn to the best resolution sea surface temperature data that we could find, and that's the head-eye SST data. And again, this shows the same thing only for the trend since the late 19th century until the present. And I think you can see a remarkable agreement in the pattern. Of course, the amplitude of change is bigger in the 2 times CO2 run than in the observed historical data. But because we normalize this trend by dividing by the global mean change, the pattern looks the same on the same color scale here. And you can see very clearly that not only this cold patch in the subpolar North Atlantic is actually observed, but also this warm patch of the United States coast is an observed feature of the past climate evolution. And I think in a way this is a remarkable success of climate modeling, that the response predicted by the model to a CO2 doubling or CO2 increase in more general terms corresponds very nicely to what we can actually observe in terms of the sea surface temperature changes in the North Atlantic, and actually also including the South Atlantic, which shows an above average warming, which you would expect from an AMOC slowdown because of that bipolar seesaw effect. We also looked at the seasonal cycle in this cold blob area, the subpolar Atlantic, and not surprisingly is what we would have predicted if it was a result of an AMOC slowdown. The cooling there is most pronounced in the late winter, early spring. That's where you see the minimum in this trend there, and it's least pronounced in summer, autumn. And that's, of course, because in the summer, you get a shallow mixed layer forming at the surface, so the sea surface temperature responds strongly to surface forcing, whereas in the late winter, early spring, it is more responding to the AMOC changes. This is a time series that we now reconstruct with these new data. First, there's many curves on this. Let's first look at the light blue and light green downward trend here. This is simply from the CO2 doubling run from GFDL, where the AMOC index is the light blue one, and the actual AMOC is the light green one, and they're calibrated with this calibration curve from the other models, from the CMIP5 model, so you can see the same calibration holds here as well. The downward trend is the same magnitude. Of course, this GFDL run is just a CO2 doubling, so it cannot be expected to reproduce the past history, including decadal variations. So forget about the model curves for now, and now look at what the data are telling us. That's the dark blue curve. They show this, again, this downward trend that we identified in our earlier paper, and it shows this minimum 1980, 1990, and then it shows this recovery, this hump here, and then again a downturn, and to record low values actually at the most recent end of the curve. Now we can compare this with the measurements of the AMOC from the RAPID project, which started in 2004. And that's this linear trend here that was also shown by David already. This is a very steep linear trend because, of course, you have this decadal oscillation in here, which contributes to that downward trend. And then the dark green curve is actually an ocean reanalysis product where a model assimilates a lot of observational data and reconstructs the AMOC in this way. And that tends to also agree here for the length of the existence of that green curve with our very simple SST-based AMOC index. Now, let me come to a final point. Let me return to these coral data that I mentioned early on. This is again from the GFDL model, and they concluded, looking at the bottom temperatures on the North American shelf here, that an AMOC weakening leads to northward warm Atlantic waters penetrating here at the bottom onto the shelf into the Gulf of Maine in response to the AMOC weakening. And so they're replacing the cold Labrador slope waters that used to be there, and when the AMOC weakens, these warm Atlantic slope waters move in there. And now, as it happens, there is a proxy record from cold water corals from exactly that area, published by Sherwood et al., now already quite a few years back. That is their location, and that is here their proxy reconstruction of nitrogen-15, which they take as a water mass tracer. And that little black curve here at the end, that is the green curve that I plotted on top of the blue and red curves in my earlier diagram with the AMOC index, where it agrees very well. And they have a few more extra coral finds from earlier on. Unfortunately, there's only 4 data points, so it's limited significance, but it is noteworthy that none of them are anywhere as low as the most recent values in nitrogen-15. And the authors, Sherwood et al., quote from their paper, concluded that the coral nitrogen-15 is correlated with an increasing presence of subtropical versus subpolar slope waters over the 20th century, exactly what the model by Saber et al. Described. These two authors, by the way, didn't know of each other. I connected them after I had read both papers and found they're talking about exactly the same thing here. And Sherwood et al. Concluded also that this persistence of warm nutrient-rich regime since the early 70s is largely unique in the context of the last approximately 1,800 years, which would agree with what we concluded based on Mike Mann's surface temperature proxies. So let me come to my conclusions. The AMOC slowdown has a characteristic fingerprint which doesn't only include this cold blob that has been talked about a lot, but it also includes this warming patch off the United States East Coast. And like this cold blob, this warming is actually observed in the sea surface temperature data that we have. And we use the CMIP5 climate models to check whether that sea surface temperature AMOC index works, and that was confirmed. Very high correlation in the CMIP5 models. And I would argue that there is evidence for a significant, likely even unprecedented 20th century AMOC slowdown is mounting. Thank you very much.
If you're seeing warming off the US coast there, is that also reflected in precipitation or storminess records on land there? Would you expect that even?
I won't speculate on this because I haven't examined it.
Okay, sure. There's a question up there. Oh, gosh.
Over the last 25 years or so, I've done a lot of model simulations of AMOC changes and looked at a lot of models, both in paleoclimate and modern context. There is some impact on global mean temperature. It's not the major thing. It's relatively small because the AMOC, of course, primarily is shifting heat around. It's not changing the radiative balance, except for the fact that it does, of course, have an impact on sea ice cover, which leads to an albedo change. And that has, of course, a radiative effect. But the other thing is that temporarily, of course, it taps into a heat store in the ocean, so that as a transient, which could last, 100 years or so, it can also have an effect on global mean temperature. But generally, I would say this is quite small, a few tenths of a degree or so.